Thank you, thank you.
You all set?
Yeah, we're good. We're good to go. So, welcome all to the last of this 10-part series. You're going to hear from me for a few minutes because I haven't said much at the beginning. It's the last of the series, but the first in MIT is bringing together facilities and students and their teachers. Like, I have a poster with me that I wanted to share that's from this Build a Net Zero Future new major for the CE department in East. That's a good indication that we are beyond this group here, taking steps to build net zero MIT. So I wanted to start off by, first of all, thanking facilities. And by the way, this is being recorded and being shared with the folks at facilities after who couldn't be here today. So that's why I'm saying all these words. I wanted to thank the people who made this lunch series possible. First and foremost, Paula Tierney and the staff here at the CUP, and also Keith Diggins and Charlotte. Next, I want to thank the students, you all. We are, both the students and Julie and I, not trained in energy systems, and so we are novices in analyzing buildings data and designing net zero buildings. However, we have what it takes insofar as we've been sincere learners in progress. Thanks also to all of you for your final presentations last week. Our DLab class gave 4 presentations, and we were happy to share that with some folks in facilities. Those were on MIT buildings, data cleaning, and energy in the buildings visualizations, carbon offsets, climate justice in STEM education at MIT, and mapping vulnerable water supplies in Massachusetts due to toxic chemicals. So today, Udita and Alex, to my right and left, will give the 5th of the student presentations. Udita has been an intern, was a student in 2022 class, and she's worked for the Net Zero MIT Buildings Project for over a year with her data analytics skills. And Alex is a student of mine also from 2022, who completed her MIT PhD in quantum computing a few months ago. Very proud of her. So they'll present their work on MIT Energy Systems Ethernet model. And finally, Rick and Judy and Amro, I want to thank you all for being marvelous mentors to our project. Rick is going to speak today on science and technology behind HVAC design for clean energy grid. And our DLab work for the past 3 years with Rick and the past year with Amro has made possible what we've been able to accomplish so far. It's a long journey and we're just starting, but we've made good progress and we're happy to share that. So without further ado, Alex.
Thank you, Susan. So today we'll be presenting on PetriNet energy system and our PetriNet model that we have spent over a year developing now on advancing rapid decarbonization on MIT's campus. I'm Udita, and our mentors, as Susan pointed out, Rick, Judy, Amro, and of course, Susan and Judy. So yeah, moving on.
For most of the next hour, we're going to be listening to Rick's excellent presentation, expanding our knowledge of heat pump technologies with a particular focus to how those technologies are relevant to MIT campus energy system. But before that, briefly, Udita and I are going to talk about the simulation we've been working on to model the effects of different decarbonization technologies applied to MIT, with a particular focus on heat pumps.
So a little bit about our PetriNet simulator. Cost optimal solution planning. A complex problem, including numerous thermal equipment, system approaches, both thermal and electric storage of various types, and rather complex utility future cost models, all applied against projected weather patterns. The ultimate goal for this project is to make a GUI interface, a graphical user interface, where the user can pick between different decarbonization strategies and see how adding them affects greenhouse gas emissions, energy inefficiencies, and expenses. Various levels of exhaust and hot water waste energy recovery will be modeled, including those currently available and new technologies just now reaching the market. The result will map energy flows and usage of all utilities, lost energy via building envelopes, exhaust makeup air, hot water generation, distribution losses, building mass, thermal storage, etc. In particular, to accomplish this, we are using a type of model called a Petri net, which we'll say more about in a few slides. A bit about our modeling methodology. Our general approach is to begin by modeling the current CUV system and validating it with data. Once we are confident that our model is working right, we will tweak it to include decarbonization technologies. To validate our model, we are making sure that it can capture the energy consumption dynamics of the system, and we're comparing our modeled greenhouse gas emissions to the CUV dataset. Now, to perform this validation, we're using energy consumption data from the PI system and greenhouse gas emissions from the sustainability dataset. For some context, MIT CUV system is the central utilities plant, which is a combined heat and power plant. And the PI system we currently use is a database, which gives us access to the energy usage data for each building for electricity, steam, and chilled water. We'd like to thank facilities for giving us access to this. For our Petri net model, we are starting with a fairly simple model. Through design iterations, we will keep refining it to reflect the complex CUV system. Next, our current model is for campus level analysis right now, and we will replicate the same for a building level analysis, especially for exhaust and makeup air systems, for which we just acquired building management data. Our final step would be to then compare the model energy flows without and with decarbonization strategies.
There are many different modeling methodologies that one can consider applying to our use case, but we chose a particular to use, excuse me, Petri net model. And this being a kind of mathematical model for discrete dynamic systems. Whereby discrete, I mean so much. Whereby discrete, I mean a system where you're taking a larger system and breaking it down into its component parts. And by dynamic, I mean that our model is tracking time evolution. And PetriNet models in particular have a couple nice properties. The first being that they are linear. And I mean this in the mathematical sense that the model can be represented using matrices. And the linearity of the model makes computerized optimization much more efficient than nonlinear models. And second, PetriNet models are commonly used for energy systems, which means that within our team, there is plenty of expertise in using these model systems. PetriNet models involve two kinds of objects. They involve places which store energy, such as a tank of natural gas, or a building, which is a reservoir of thermal energy, as well as transitions which move energy, such as a steam distribution system for a campus, or a boiler which converts natural gas into steam. It's very important to note here that the arcs that represent the input and the output of the transition have weights, and using these weights allows us to accurately represent the physical processes of the transition, such as a loss mechanism. I'm going to, in this diagram, represent the energy that's moving throughout the system as these little black dots. And now let's take a look at how this model captures time evolution. Let's consider starting at some initial time where all of the energy is at some initial place. And if this transition that I've drawn up here fires once, then the energy moves according to those weights of the transition. So time evolution can be represented by this equation, where here P represents the amount of energy at each place at a particular time. T is a matrix that describes the amount of energy that's moved by each transition, and F is a vector that describes how much each transition fires at a particular time step. So this equation just represents the motion in the diagram that I showed you a minute ago, where the energy at each place at a certain time is the location of the previous time step combined with the time of the transition. So when we're working with a PetriNet model, there are three steps that we're using essentially. We are creating the PetriNet topology such that it represents the places and transitions in the system that we're modeling, namely MIT's CUP and energy distribution system. And then we're constraining that model using building energy consumption. And then we are running an optimization in order to understand the energy flow and also the greenhouse gas emissions produced. The model contains three components: the CUP, the distribution systems, and the building consumption of energy for electricity, for steam, and for chilled water. And if we break down our model of the CUP, it contains the natural gas input to the system, as well as the combustion turbines that use that natural gas to generate electricity, as well as electricity pulled in from the Eversource grid. We also include the boilers that generate steam and the chillers that are used to generate chilled water using both electricity and steam. Finally, a very important part of our model is the generation of greenhouse gas emissions, which come from the combustion turbines and also from the boilers, which use natural gas.
Using greenhouse gas emissions to validate our model. An integral step in our model is calculating greenhouse gas emissions, particularly carbon dioxide. Now, how do we integrate this in our model? The PI system gives us energy consumption data at a 5-minute granularity. The sustainability data pool data gives us monthly energy usage data and the greenhouse gas emissions associated with it. I'm proud to say we are in the process of validating more complex versions of our model. For these validation trials, we chose select buildings, largely representative of the campus, with the time frame of September 2019 to December 2019. We chose this time frame for two reasons: because it was a pre-COVID time and we had full data available to us. Once we had our data sets ready, we converted the PI system data from 5 minutes to daily granularity, and we're running the model to calculate GHG emissions based on the firing of turbines and boilers, and are then comparing the sum of model calculated daily greenhouse gas emissions to the monthly data we have from the sustainability data pool. It was important for us to also explore the greenhouse gas emissions we were using, since it is ultimately what we're feeding into the model and using for validation. And hence, we decided to graph the MMBTUs consumed by building against greenhouse gas emissions reported in metric tons per CO2 equivalent, and then fit a regression to examine the data trend. As you can see, all data points which represent buildings are on a straight line. It's a linear graph, which suggests that there's multiplication happening of energy consumption data by a constant factor instead of using natural gas consumption. This seems imprecise, since there are multiple possible energy sources, input sources, and paths. We are convinced that this simple calculation does not represent the reality of greenhouse gas emissions and is therefore not precise enough for our model. Hence, we need more data, maybe different and more accurate data from the CUP to validate the model. Thank you.
You should have seen it yesterday. It's much improved. Now we have Rick and Judy to give the presentation that we saw yesterday, and we're looking forward to it. And thank you all on Zoom for coming. We're happy to have a pretty big crowd today.
Hi, so I'll pick up. And so as you heard from them, we don't have enough data yet to convert natural gas. And we just got data to try to understand some details inside the buildings. So we just got some BMS data trying to decipher exactly the exhaust systems and whatnot. So we're sort of getting this data together. We're not there yet. So about us in particular, and about me, we're sort of a mixed bag of people who accidentally landed in the geothermal heat pump business. So we're HVAC contractors. I'm a licensed engineer. I do R&D. I'm also on the Binational Standards Committee for Geothermal Design Installation, which there's a really good revision coming out at the end of this year. And, you know, I play a lot of roles just so you realize where we coming from? I got to figure out. Oh, there we go. It worked. So in this, I want to resolve what I would call excuses. And I'm sorry, it's maybe a bad connotation or whatnot. Excuses not to decarbonize it. We hear really all the time. You know, we've heard this from folks at MIT and Harvard. We hear this in my private practice here from engineers and architects all the time. It'll cost too much. We don't have the technology, and the grid can't support enough power to decarbonize. I want to try to answer these here, and I hope try to convince you that that's not true. None of those are true. So this was just the news from just a few days ago, just to make sure that everybody understands what the point of this is. This is ocean temperatures, and we folks are in some dangerous new territory. This is really, if that doesn't scare you, you are asleep. So we had to look at this yet. Don't try to understand this yet. We had this amazing, interesting experience. Went to the New York Geothermal Conference 2 weeks ago, and ended up, this is why we were there. We were there showing a product, and ended up showing this work that we're doing with the D Lab. And everyone who's a leader in this field, all kinds of engineers, designers, and everything, you know, policy people, all sat down and looked at this graph, and we're really kind of blown away by it. So in the course of this, I'm going to build that graph and try to help you understand what's there. I've sort of realized, okay, there's a lot more there and a lot more good there than we thought. And so I'm going to build that. So just to show you, we actually have had our feet in the dirt for, you know, a good bit of time. We've got systems ourselves in for now, I don't know, 13 years, maybe 14 years, I guess, systems, some of which we haven't seen in a long time, and we know they work. And I thought this, and then so somewhere between when we got in this business, which was back in 2007, when we got invited to do the Chancellor's House at University. Then we got some stuff I'm going to show you in a minute, and ended up at MIT winning this Climate Co-Lab Award. I thought this was kind of interesting because Steve was there. But this thing on how to decarbonize MIT's campus. And very interestingly, not a lot has changed at all from what we said in that presentation. I think, if anything, it's all proven. To give you a little more credibility of what we know and don't know, maybe. We've done this work with Oak Ridge National Lab and gotten validated a technique that I brought to the table in this industry of how to more advancedly understand and model the ground. Basically, I'm a computer engineer, so I connected some electrical engineering paradigms with ground thermal and realized, well, this physics is all the same. You can model it using electrical equations. You'll notice the blue is actual data from doing a thermal injection test. This is how you test the ground. The green is the mathematical model. And while you can't even see in this green these variations, you start applying some math, some like, and this is a differential analysis here, running differential, you start seeing things like groundwater movement. Now, this mathematical approach, the people in this business have been doing this for a long time and doing thermal conductivity testing by taking a line slope analysis on this. Nobody has been calculating heat capacity or diffusivity. They've been guessing that from well drillers' logs. So we're bringing some new science to this, and you can see when you vary the power, this thing all tracks it, and it starts finding out what are these details in here. So it's some good stuff. In this conference 2 weeks ago, one of the two people who founded the North American geothermal manufacturing industry gave this presentation on the tax credits that have just been passed. And this is an example, and I'll walk you through it. So this one's for a nonprofit entity, which applies to MIT, all the cities around Massachusetts, all the schools, all this kind of stuff. Take a system that would cost $500,000 more. See, this is geothermal versus conventional. Cost $500,000 more, less than utility rebates, and I'm really pretty sure that your Mass CEC rebates are a lot better than that. Cover design. This tax credit has a 30% thing, a 10% bonus for manufacturing in the US, which these things are, and these pieces of equipment are, and a bonus for energy community, which applies where they shut down coal plants, but it also applies to brownfields. And if I'm not mistaken, MIT is a brownfield. So that's something to find out. You know, how much of the property is a brownfield? How much can be claimed as a brownfield? That's what that last 10% is there. The bottom line is this would, in this situation, the system costs $500,000 more, $475,000 after, but it would turn a profit in year one because of the tax credits. So this is a new kind of territory. It's a new territory already with these systems, but in this case, you've got this instant return on investment. Basically, the government, and I'll explain this in a minute, the government is paying you to do this work, and there's a reason for that. So just to show you something else, there's other models here. You can find this, just Google Climate Master tax calculator or whatever. You'll find this stuff. It's online. Even better for that, there's an expert in your town, this man, Jerome Garciano, who is a real expert on tax for renewable this and that. So I'm not sure if he's completely up on the geothermal yet because the rules have not come out. They're going to come out soon on this particular part. But he's the go-to expert across the country for large parts of this. So you got him right in town. Look him up. So this is how we ended up in the Climate Collab. This engineer, I saw this presentation 2 years in a row from this guy, Don Penn. He had already put in like 100-something geothermal systems in Dallas at this point. And then some ARMA money came out and they said, can we make this a zero energy building? So he thought about it and came up with some sort of breakthroughs in a way. He said, okay, I'm going to apply some new engineering approaches. And he realized that with the geothermal, he could eliminate the mechanical rooms, eliminate the steel pipe, which is a really bit of a radical thing, but it's completely true, and put in all these small distributed units and fully distributed pumping. In order to get rid of all the central pumping, all the everything like that. Sounds radical to a lot of big systems engineers, but this is what's going in. This is what's in the King Open Center right up the street from you and a lot of other places, this kind of approach. I believe it's King Open's like this. Usually these things are horizontal up in the ceiling, but they're the same box. And for those engineers who flinch at the idea of getting rid of steel pipe, here's an example. This house was at a hurricane, wiped off its foundation entirely, and there's the geothermal system still attached. There's a water-to-water unit, pump package, and the HDPE pipe. This is a really high-grade HDPE pipe, thick walls, still attached to the ground. This stuff has an unknown life. It's been in use over 50 years in pipelines. It has an unknown life. The official word is over 100 years. In reality, nobody has a bloody clue how long it'll last, but it's going to be a long time. So in this building, this guy, Don Penn, he figured out how to put in the geothermal system, really advanced geothermal system at the time, for the same cost as a conventional system. And that was getting rid of the steel and getting rid of the central pumping. So you notice these are this bottom one is the 4-pipe conventional. The 4-pipe means chilled water and hot water or steam. And then the geothermal is a 2-pipe system, and in this case, plastic. Same price to start with. You add this cost of solar, and basically this thing ends up turning a profit over time. Breaks even really fast with the solar. So this is like a new world. And this is why we ended up the Climate Collab, because it was like, I saw this thing the second year in a row, and he said, oh, and it's going to break even faster after it's running it for a little while. And it's kind of like, you got to think about this. This is a new age for man. We used to pay for energy for buildings. Now we just install good equipment and the buildings pay for our energy. It's interesting. The equipment does it for you if you maintain it. So this school is this Lady Bird Johnson. It's one of a bunch of schools studied by NREL after that. And you'll notice the EUI on this building is negative. This thing produces more energy than it uses. I thought this was interesting. MLK School, Boston. I did a Google, and in 2018, this school opened right up the road in Cambridge, right up toward Harvard Square toward the river. And I've not heard anyone even mention this school. So this is kind of interesting. I wonder what's out there. But they've got, cutouts in the corridor so you can see mechanical and system and such. Where's this school? So here's another good example by a trusted source, ASHRAE, the Mechanical Engineers Society, which I'm in. And this is a building in Atlanta. Their former headquarters that they went, okay, we had a lot of opinions about geothermal and VRF, air source, high-end air source. We're going to settle it. So they built 2 floors in a remodel, 1 geothermal, 1 air source, very equal. And this was very well studied. And this is the model. So the red is the temperatures outside, measured every whatever. And the blue is the ground loop. Now, in Atlanta, I happen to know that the average temperature is somewhere down here. So this blue ground loop is running above the average air temperature, which is a little hot. That's where it should be running. So, what's happened a lot of times, people go, well, the geothermal is not keeping it cold enough. And so they go right in this area here and apply some sort of a chiller in the summertime. That's not how you do this stuff. This stuff is an annual battery. It's an annual cycle battery, the ground loop, big chunk of earth. And the way you tune these things is you tune them right after the winter bottom. You start bleeding off heat like at night in the spring when the power's cheap and that evenings are cool. And you could do this with, an air source, dry chiller. You could do it with just ice melt loops under sidewalks and parking lot. There's a lot of ways to do it. Like, for example, this is a giant box IKEA in Denver that's net zero, and they're doubling. This was in the news, just at doubling. They're going to double the solar arrays. It was already good. The giant, look at the size of the cars. This is a huge place. This place has a geothermal system that only has something like 27 or 30 something wells. I can't remember the exact number, but it's something that you just go, that is stupidly small. It doesn't make any sense at all. But it's because this place has a bunch of restaurants in it, so it's too much heat. That's their problem. And so though it's a geothermal advanced system, most of the thermal system is this giant radiator there they poured the concrete under the loading dock. So this term geothermal, when people like me come to the table and say this, it's not geothermal like drilling wells in the ground. It's whatever is the thing that makes this system very efficient. So I think it's good to understand a little bit. I know we've ruffled a lot of feathers and people think we're coming in and complaining and all this kind of stuff. So I thought it would be good to kind of explain where we're coming from. This is where we're coming from. This climate action thing is critical for the planet. Even on the best case, if we all get our act together, we are not in a good situation for the people who were born recently, who are going to outlive us. So this is critical, this IPCC climate change type stuff, and the world is completely depending on us, some of the leading engineers, to pull this stuff off. So here we are. We happen to be geothermal experts by accident. We're alumni. And so we're working this. Collectively, we're working this. We've been trying to influence things at the owner level. And since we won that equation, they're involved in this. But we have found that there are certain industries that were sort of, pulling the strings on the board behind the scenes. And so administration's been unable to really do a lot of stuff. And it's just the way it is. This is what's been going on the planet. I believe those factors have been silenced to some degree, I think. Okay, campus is a test bed? Yeah. Well, we've not really seen it yet, except in the Met building, by the way, which I'll get to is an excellent example. So there, administrations, depending on the engineers, you guys a lot. And you guys are depending on your expert engineers you turn to. And unfortunately, from where I'm standing with what I know they listen, every engineer I run into is an uninformed engineer on this topic. You guys probably know a little less than me, and you're way more informed than most engineers on this topic. There are very few people who understand this. And these people, most engineers, go after decarbonization via heat pumps, but they don't really understand decarbonization via heat pumps. So, take the Met building. This is a great example. You guys have shown, not only if you go to heat pumps, this is a heat pump-based building. Not only if you go to heat pumps and you do a good building with energy recovery on the ventilation and such, you end up with a building that really is cooling dominant, very classical commercial building. Granted, it's not a lab, but it's very similar to a lab in some ways. And this thing clearly can be run by heat pumps, and it is being run by heat pumps. These are from you guys' slides. And I'll get back to that heat pump again and explain a little more about it. So everything is here is perfect. And I believe you guys are picking pathway 2 is what you guys are doing. I just want to point out pathway 3 and explain, this whole thing of using a water source heat pump, that's what these are, water source heat pump. With the chilled water return, the only advancement here, and this is a conceptual advancement, is we're not talking about chilled water return. We're talking about an ambient loop. It's just a terminology change. It's a mentality change. It's the same pipes, but you change the limits on the temperature from 45 to 55 instead to 45 to 90. And that's it. That's the limit of the change. That, however, is a big conceptual leap for a lot of engineers. So that's the deal. And we've tried to talk this through here, and we've realized, okay, this is just engineers competing against engineers. It's not the way to do it. So this is what the whole project is about, bringing heat pump design tools to the table to just bring this knowledge and the ability to quickly manifest this, to cancel these people. And I'm not pointing a finger at any particular engineers. Believe me, there are a lot worse engineers I could give you numerous examples for in our town here. We want to make this so that any activist out there can do this. This is for us a climate action thing, and we're trying to figure out how to make this climate action happen quickly. So the overall goal is an En-ROADS style simulator. If you guys haven't seen En-ROADS, I really encourage you to look at it. This is a Sloan spin-off product. And where our thing is, we've got software together, we've got this software running, and we've got the Petri net running. And what we have found at this point is we just do not have enough data to calibrate it at all. So we don't have anything that we can put our finger on. So geothermal, yeah, geothermal. Okay, people do geothermal, but then maybe you don't do geothermal. So here's right on the far side of Tech Square, the new Moderna building. If you zoom in on that backyard there, you'll see these are that's a well rig. And you can see from the shadow, you know how these Google things are, they're two pictures combined somehow. You can see that shadow, there's actually a boom standing up there. This is a mud rotary system drilling, and you can see this is what's coming out of the rock under you guys. It creates this fine silt byproduct from the argillite under you. So what we found listening to area consultants is these boards you should figure are going to cost you $80 a foot. Okay, this is real simple when you're in this business. $80 a foot to drill, forget it. It's off the list. It's just that simple. You don't even go, oh, well, but we should, this, that. It's too much money. We spend like $20 or less here. And if you were doing a volume like this, you'd be spending like maybe $16.50, something like that, all over the South and the Midwest, the middle of the country and all. So that's just kind of crazy bad. You wouldn't do it. Here's another thing that engineers do. They go, oh, you got to separate all the pipes all over the place. So they create all this work and all this extra money. This was the Chancellor's house, the first one we did. And it's just a joke. I've seen this engineer do this multiple times. It's just silly. Here's another job. Notice this is a well log, a well driller's log. And you notice water, 20 gallons a minute, water, 20 gallons a minute, water, 30 gallons a minute, water, 20, water, 10. Look at all this water. Then you only drilled this test well. This is a test well to 295 feet. Now, if you're a geothermal guy and you see all this water, you go, hey, standing water column, reinjection, standing water column. There's all kinds of water-based, especially in mountain water. This is beautiful water, you know, based things. Well, no. So this engineer spec'd doing 450-foot wells. So he tested 295 feet. Spec'd 450-foot wells, air rotary, because it's hard rock, and this is what you get. So this stuff would block, this is the well truck, the drilling is this one over here. It's off the screen drilling, and the air is forcing the water up in geysering. So this just turned, and this stuff would block and go down and rock. See the rocks on top of the truck would blow out of this. This is insane. Created a complete disaster. The driller lost his shirt on this. And the reason for this was neither the engineer, nor the driller, nor the contractor had ever done geothermal. We were the only people who'd done geothermal, and we were just there for a small part of this, doing the headering and the run-ins. So anyway, this turned into a complete disaster. Even this was the last trench, even that just turned a complete disaster. So the bottom line is, the bottom line here is that you're really, if you're doing geothermal, if you're in anything but competent hard rock, then you really have got to involve somebody who's got the right training on it. Yeah, you can't go look at what somebody else did at another place and just go, oh, I'm going to do the same thing because it's in an ASHRAE manual and think it's going to work. If anything is different, competent hard rock, you're probably okay. Anything else, don't do it without somebody who's got more expertise. So there is this training program for engineers, and there are 1,000 something. Last time I counted this, my number's like number 300 something. And then there's people like this. These guys are some of the 40-year guys in the business, and their entire business is going out fixing errors by other engineers. So there's a lot of resources. The standard I referred to, this binational standard, is an excellent resource to cite in your documents if you're doing stuff. Okay, so you don't want to drill deep right here in Cambridge. So we found some test bores here. These are geotechnical bores. By the way, that school is right there at ML Page School. And looking in a little closer, we found that this one right behind Kresge Auditorium found this particular bore, went all the way to bedrock, supposedly. And it looks like this. This is, just the typical kind of bore that's done for new buildings. So these are all over the place. There's all kinds of records on this. And you'll notice that, because I've cut this up, this is multi-pages cut up. You can see, so it goes to depth. It's a bunch of clay. If you look at the other ones, there's a bunch of sand and clay. And then they say top of bedrock. But if you look at the note, this isn't actually top of bedrock. This is just some loose stuff down there that's above bedrock. The bedrock is like another 15 feet down. You'll find in other bores. So what's in that? Is that a possibility for standing water column, water flow? There's a lot of water here. This is totally saturated, this ground. I guess I didn't show that, This ground that is a floodplain. That whole thing is nothing but a river floodplain that's been filled. So this is a completely saturated ground, hyperconductivity. And these particular people at the show we were just at, this was somebody launching in the US, a product developed in India, Mumbai, where they're actually putting the heat exchanger down the bore, all in stainless, to get rid of the issues of like bad water you don't want to mess with. I heard somebody mention that about bad water. You don't want to pump the water under MIT. And it's like, well, but if you just pump it over there and you reject it over there. So my point is not that there's a particular solution, but that there's a class of solutions. It's about the mass. So Paul Ricci and we did a just back of envelope kind of analysis on is there enough mass? If you just say, okay, let's go for a 22 delta, just in that 100 foot of overburden that can be extraordinarily inexpensively drilled with no mass to speak of. And my back of envelope calculations, which I wouldn't stamp or put my reputation on, came to 18% of the campus area. So this is kind of a limit. This might suggest that that's the most you'd need. And the rest of this, I'm going to show you a little different. So just for completion, I want people to know, like if you're out, you got a set of ball fields or something like that with some buildings next to it. People do this sort of approach, which is a slinky. It's called a slinky coil. Do you see those coiled pipes in there? You can do that in trenches. You can do that in big areas. You can do it in individual trenches. And then like a lot of places under ball fields, people come in and do this. And you can drill down with horizontal directional bore, clearly all in that 100 feet of overburden clay. And they do this, it's a mud rotary with bentonite slurry. And you bentonite the thing back, so there's no structural issues. You pump in bentonite that hardens, you restore the clay when you're done. And you can do this in layers. You can go down, they detect where they are. You can go down and do this in layers. So you can get a huge chunk of earth, even just under West Campus with this approach. Okay, that's enough for geothermal. Showed you a bunch of options, a bunch of different ways, and trying to just go, it's not about drilling deep. It's about using the mass of the earth as needed. So in Boston, here's a graph of your weather for, I think this was Holcomb, one of the Air Force bases in town a little bit, not Logan, I think, not sure. And you'll notice that the lowest temperatures here are well within the modern cold climate air source heat pump range. So in reality, in Boston, you have an air source heat pump solution with the modern advanced stuff. And I've stood in front of one of these things when it's cold, and you do not want to feel the air coming out of it when it's cold. It's painfully cold. They're very good at actually extracting heat out of air. So with that, let's start trying to build this graph just a little bit. So there's 2 points on this graph that we've shown you. The GRF, which has the lowest operational cost because it's got this massive thermal battery anchor. And you got the VRF, which has a lower installation cost, but a higher operational cost. These things over here are just not zero carbon solutions. This involves thermal storage. So over here is thermal storage. This is, these are things that you can't build the grid with this low end air source heat pump and such. So, we'll keep going, running out of time because we lost a bunch of time. So this is a study out of Canada, what it would cost for the grid to do geothermal versus the high-end air source. And notice it's the high-end air source, except in Vancouver, where it's very mild. And you can see their conclusions, it would cost about twice as much to do the grid. So give you a reality check on that. This shows you why geothermal, why the government's sponsoring geothermal, because we're not going to get to a 2050 solution without this thermal storage anyway. And then just to go back to that ASHRAE model, what you just saw the ground loop before, This is their actual data collected. That red is the air source heat pumps for one floor. The blue is the ground source heat pump, and I threw in this blue line, which would be that if you tuned the battery, tune the thermal battery, and you can see 2 to 1. So you get this, that in fact, the geothermal in the winter peak, so this is, oh, I'm sorry, let me explain this graph. So cost, power used. This is instead of over time, this is converting the model to over temperature. Okay, so this is the hot summer, and this is the coldest winter. So this is the winter peak, the thing that you have to build the grid to meet. And you can see that's going to take a lot more electric batteries than that. And that's the key. That you put in, instead of just using electric batteries, you put in a thermal battery. And the gig is that those electric batteries cost a lot of money, and the thermal battery costs less. And it's this because they're at least 3 to 1, and then you got a 2 to 1 ratio. So I haven't thought this through completely, but you get the point. You're going to spend a lot more money on electric batteries rather than these thermal batteries. So that adds this factor. It's grid cost. There's some kind of much more cost up here for air source heat pumps than for geothermal heat pumps because you're putting in that battery. You spent some more on installation. But remember, that pipe's going to last forever. So what you spend on this installation, which, by the way, right now is down here because of the tax credits, but that stuff is going to outlast the building. This stuff is permanent infrastructure. So it's really property value and not cost in a way, you know? So you get this much lower grid cost for it. And what I'm going to show you from here is there's another class in here that's less expensive than the deep geothermal, that in fact is going to do even a better grid cost. So now let's add power. And this is sort of the final piece to seeing this. So right now, wind and solar are by far the cheapest power, and that's why they're going in like gangbusters. And the gas turbines, while they're the next least power, they've got to go away, or they got to be on another fuel, or they're going to one or the other. And so we're really in a world where this solar and wind is going to be the thing. And then if you look at, by the way, this is Lazard. And so if you ever want to look this stuff up, these are the go-to authority that everyone cites, Lazard. Just go Lazard, LCOE, levelized cost of energy, and you get a whole document on this. With the tax credits, which is this one, you get some of this amazing marginal zero cost of these systems. These things are going to go in like gangbusters over the next decade. And it's just going to fundamentally change the marketplace. And here's an example of what's just, notice the dates. These are all really pretty current. That Lazard was March. And so, there's a lot of this going in. Now take a look at wind. This is wind, daily production over a lot of days. And notice there's some lot of wind, and there's some really bad low wind, zero wind that might even last a while. And certainly if you cut it all across here, there's a lot of periods that last a while. And even within a day, wind can do this kind of thing. Even some of these days, they can go up and down and up and down. Solar, the same kind of thing. You'll notice if you look at the capacity, you go, well, we got a lot of capacity and we're getting down to almost full capacity. But when we start looking at it over a system over time, you see that this thing has a lot of holes in it that are going to have to be dealt with. So there's going to be batteries for that. The key here is batteries of some kind, electric or thermal, or thermal. The key is that by 2050, we will have built this much PV to get the system to work right. This is basically what everyone's projecting. So there's going to be massive amounts of excess PV. And this is already happening. California has already hit zero and gone below zero. And even during that zero, there was curtailment. Solar, as in cutting it off the line, you can't use it. And it's like over the year so far, even there's all kinds of curtailment. And then when you look at the cost, the marginal cost of power in California, you see there's just this wild thing, but an awful lot of this is negative. As in, like, they don't want you, if I understand this correctly, and I'm not an expert in this stuff, if I understand this correctly, that means they don't want you to connect to the grid because there's too much power already. We already know there's periods where there was too much power and power was free in Texas, actually some while ago from wind. So this whole thing of too much power and too little power from the wind and solar are both on the table. And presents this giant opportunity to run these thermal batteries. And so let's just advance this one instead of just thermal storage. Yeah, this is, now let's expand it. This is all heat pumps, and this is with thermal storage. And so you've got this first bar here is with water tanks, and engineers have been doing those for a while, especially in the summertime, like above ground. There's this other class of solutions in between. Let me show you this. So let me just patch those three in. Okay, real example. Well, it's in, let me just quickly fast forward this. Real example from Asheville. This is what's going to happen if everyone electrifies. Add the solar to it, you get this curve down here. That's this curve, VRF. Add a water thermal battery, just a water thermal battery. This was modeled on a 3 foot by 3 foot by 7.5 foot cube in people's basements. And you get that one. And you see what that's done to the peaks. And that was an extraordinarily dumb calculation right there. And then if you add the geothermal, you get that. That's basically how these three add up. And so the bottom line is that there's some class of stuff in the middle here, in this area. There's this new class of batteries just being tested now that are smaller. They're not deep bores. They're like, 2 and 3 foot diameter bores. This battery just went in University of Illinois as a test by Xiaobing Liu, GOE's top guy in this field at Oak Ridge National Lab, who we did that work with. And so this thing is a combination of a bore with a water tank around and some phase change in between. And you can loop both of these. And the deal is that this is a 3-in-1 battery. It's a water tank, so you get that quick energy that you can store and pull back in a day. You get this phase change battery, so you get like a couple of days storage maybe, or whatever, a longer storage in that. And then you're connected to the ground. So this battery does all three things. It creates this perfect situation right in the middle. And some mix of this battery for different situations is probably going to end up being the goal for how we actually design these systems in the future. You might have some deep battery, some deep geothermal. You're probably going to have a bunch of these short geothermal things with phase change in them. So that's going to create this optimal point. And that's what we're looking for with this software, is how do we design that point? So I see that we're out of time. So I just want to point out real quickly, people I know how to model this stuff. So even in the Great Court, for example, you could put in a geothermal system, design it so that the therms never get to the sticks under the buildings that are in the mud. And it's easily done. And we even have the software to do that and could show you. I'm just going to skip this for right now. And just one quick thing about these buildings. Building 76. We'll take 1 minute. Yeah, go ahead.
I'm just saying that please take 5 or 10 more minutes. We're not going to walk out on you, and we want time for those who are on the Zoom call to ask questions if they can stay.
And if anyone wants a follow-up on this, please just let us know. Be more than glad to take the time and go a little more in depth with this, a little more carefully. So the biggest energy consumers on campus have to do this exhaust. Right? It might not be the biggest, but collectively the biggest is exhaust. This is a cancer lab. It's 100% exhaust, 100% makeup. We studied the building a little more to see if there maybe were some other factors involved. This was sun. Viviana did this analysis where they tried to map out the sun from the weather data and see if it correlated. And it does to some degree, a little bit, but it's not a lot. An EUI, this is an EUI-based thing. Basically, this is strictly a wet bulb air-based energy load analysis. I have to suck in and condition the air to be room temperature. So that's the expense. It's just going out the roof. It costs a lot of money. The same thing on building 9. It's got really some similar characteristics. So in other words, all the buildings have this same kind of paradigm in them. And that's the air system. You can see this giant air system on the roof there. And so the deal is you just have to go, okay, you got to have the exhaust because that's the cancer safety, the P4 lab safety. But what you do is you want to recycle the energy. I'm sorry for the basic artwork. Recycle the energy, and that will produce savings. And this is what is happening with the ERVs on the Met building, which granted can have a latent wheel and such, but it's the same mentality. You got to capture that back. So here, can't remember where I was going. Oh, so let me just take one thing. I just want to make sure people get it. The heat pumps are a technology. They're not a box. So these heat pumps, this is what's inside. Here's the way a bunch of them look. These things are all the same. They're all a compressor, some piping, some valving. Sorry, I've got it behind this box. heat exchangers, there's an exchanger or an air exchanger, and that's it. Compressor, air exchangers, and valving. So they're all the same. And the bottom line is to get this high coefficient of performance, this high efficiency. In this case, in a ground example, you want to get 5 units of heat value for 1 unit of electricity. You got to find 4 units of energy somewhere else. This is the principle behind all of these. You got to store that energy when the power's cheap, when the air's the right temperature, put it in the thermal battery, suck it back out. It might be you stored it in the spring, use it in the fall. That's a ground battery. It might be you stored it this morning or overnight, and you're using it in the day. That would be a water battery. So, and then the mix in between. And these are not mythical. They're deterministic. And you can see here, these things have actual known coefficients of performance. And this is exactly how you diagnose these things when something's wrong. You go to these tables, you go, is it performing like the table says? So this is a very deterministic building, not a guessing game, not opinions. And so have we answered these? Too much decarbonize? I think we've said that. It'll make you money right now to do this geothermal stuff. Do we have the technology? Okay, there could be some questions on the table still. So I went and looked up Bunsen burners, which is the only thing I can think of is a real question mark here. And it turns out there's a bunch of things out there, electric, there's some other gases, a bunch of papers on it. If there's anything that MIT would excel at, it'd be like eliminating the Bunsen burner in a really cost-effective way. I think you got to say, other than maybe a tiny bit of carbon usage for things like that, you got it. And then can we provide enough power? That's the thing. And you're going to need the software for us to prove that that's the case. And so that, I think, is the deal. I can just skip that. And just to leave you with this, I just want to leave you with this thought. And I'm sorry, it's just a little bit of a challenge. But, it's a beautiful machine, brilliant development engineering. But the reality is that, skip that. The reality is that it's going to have a carbon footprint. Unless you got some alternate gas, it's going to have a carbon footprint. Alternate gas, good idea. So without the alternate gas, this will be generally obsolete in 2050. Generally, might still be useful for peaking, things like that. But is anyone going to pay the money to upgrade it in 2040 when the next refurb is needed? And that's the big refurb, unlike the last one. Is it right to spend this money? Is it smart to spend this money on the hot water upgrade now when you kind of have proven you can do this campus on an ambient loop on the same pipes as the chiller loop? And so I just encourage you to step back and learn a lesson from Andy Grove and people come before. Andy Grove is one of the 3 founders of Intel, the largest electronics company on the planet. And this book that he wrote, it's a very short read. The first part of it even is just a short read on inflection point. And believe me, folks, we're at that inflection point, certainly with this IRA. And it's the right thing to do is to take it all in and go, how can we change our paradigm to match the new paradigm that's going on around us? So, and I'm convinced there's a solution that keeps this and spins it down so you don't even need to upgrade it in 2040. That's what I think that's kind of the goal where we're going. So there you go. No, that was fast. If anybody wants a more in-depth presentation, I'd be more than happy to.
No, do we have anybody still standing from the Zoom folks? And thank you, Rick. That was great. Fantastic. We've got just Julie, Daphne, and John. Do you have a question?
Anyone?
Okay, anybody here among the students?
Very good. Thank you.
Okay, I think we were blown away, Rick.
We're confused.
No, not confused. Maybe confused. I've seen Rick give versions of this presentation for the last 3 years, and I get it this time, best of all. Okay, but it's taken me a couple of years. So if it's a little bit overwhelming for all of you, just see me. Here I stand still, and grateful to Rick and Judy and to everyone who's come and made it through this 10-part series. So thank you very much, everybody. We're off to a party, and it's a beautiful spring day, and we'll tell you all about our party, Rick and Judy. Thank you.
Rick, actually, I
Thanks.
do have that plot that you've been showing, where you have cost on one axis and you build it up slowly over the course of the presentation, and it's got green background on the left and red background on the right. I don't think I know what the x-axis is of that plot. Could you just tell me what that is?
Oh, the x-axis is just the 5 systems. You know, it's just the 5 types of HVAC. You know, here again, this was so cool because this really brilliant young guy in New York came up to the table, won one of these big grants from NYSERDA there. He came up to the table, and after about 10 seconds, he goes, "I hate that graph. I hate it." And so I gave him like a 90-second tour, and in 90 seconds, he was going, "I love this graph. I love this graph." So it's an attempt to try to pull the concepts together in one place. And he started pulling people over and showing it to them. And all. That was what really taught me that there's something more here than understanding this. So it's really just an attempt. And if anybody's got any better ideas of how you do this, please speak up, because the whole idea is, how do we move the engineering community and the building owners to rapidly decarbonize? And not pointing finger at MIT, everywhere.
Right. Thank you.
That's
Rick.
it. That's
Thanks.
it right there.
For coming. Yep. Some folks from MIT alumni. Yeah. So that's great.